Hello students, this is series of functions. So we discussed this series of functions. What is series of functions? Here this is pointwise convergence first and uniform convergence. So we will discuss about pointwise convergence and uniform convergence. So what is the definition of pointwise convergence? We assume that if fn is the sequence of functions such that fn ranges from a to the real numbers, and if another function also ranges from a to real numbers, then we can call fn tends to f, means fn converges to f pointwise on a, on this domain a, if fn x tends fx, means the all the functions of the sequence the sequence as n tends to infinity, the sequence of functions fn converges to fx for every x in the domain A. So this is called pointwise convergence, means fx can be said limit fnx where n tends to infinity for every x belongs to the domain A. So this is a definition of pointwise convergence. Now I will discuss example later. First I discuss about uniform convergence. What is uniform convergence? If we assume that again fn is the sequence of functions such that fn ranges from a to the real numbers and f ranges from a to real numbers, then again fn converges to f uniformly on a if for every epsilon greater than 0, epsilon is a very small number, nearly 0 but not equal to 0, a positive number such that some n we can find out there exists an n in the natural number set of natural numbers such that if any small n greater than this n capital N belonging to the natural numbers implies that mod of fnx means as n tends to infinity, mod of fnx minus fx less than epsilon, or nearly its supremum value, limit of supremum value, we can write limit of supremum value of fn x minus fx is equal to 0, then we can say that this sequence of functions uniformly converges to f, means they are limiting the sequence limiting the limit of the sequence of the functions must be f uniformly on a for all x. This is also we have to mind the we have to keep in mind that for all x, if this satisfies this condition that it is the sequence of functions convergence to the point to f with this condition mod of fnx minus fx less than epsilon for all x belonging to a in this domain, then we can say that fn convergence uniformly on f. The sequence of function convergence uniformly in the domain A uniformly. There are another conditions. This is another condition. This is another condition. So here are some properties also about uniform convergence and pointwise convergence. Here we are taking an example. let the sequence fnx is equal to x to the power n. We have taken this sequence is equal to x to the power n. So we can say that this converges pointwise on the open interval, closed interval 0, 1, but not uniformly on the closed interval 0, 1. So why we discuss this? Here, if we take x to the power n x to the power n tends to 0 or x to the power n tends to 1 as n tends to infinity. If x belonging from 0 to 1, the half open interval 0 to 1. So why these two values are taken by in this interval, half open interval 0, 1, we can examine this in this way. In this half open interval, if we take an increasing sequence of if we take ax is equal to n by n plus 1 in this half open interval, then its limit will be 1. And if we take a decreasing sequence in this same interval, then we can choose x to the power 1 by n, we will get its limiting value is 0. So here in this open interval, the function x to the power n can take both the value 0 or 1 as n tends to infinity. It can be 0 or 1. So we have taken these two values, and here if x is equal to 1, then x to the power n tends to 1 as n tends to infinity. So fn since for all the value for every value of x we are getting fnx to the power xn converges. So we can now generate a function f such that, or define a function f such that fx 0 or 1 if x lies between the half open interval 0 to 1 and 1 for if x is equal to 1. Then this defined function we can say that fn converges to f pointwise for every x, So this is the pointwise convergence in A, belonging to A. Now if we examine the inverse convergence, here if we take fn mod of fnx minus fx is equal to x to the power n, this could not be less than epsilon, since it can be 0 or 1. If it is 0, then it can be, but if it is 1 equals to 1 for increasing sequence, it cannot be less than epsilon. So we cannot define uniform convergence definition. So but for x is equal to 1, it will be 0. fnx minus fx, this is 1 minus 1 is equal to 0. So for this interval we cannot find out and we cannot find out any function satisfying this condition mod of fnx minus fx less than epsilon. So we have no function converges uniformly at any for all points in this closed interval 0 to 1. So we have a contradiction. So this function fnx x to the power n in this closed interval 0, 1 not converging uniformly but pointwise, converges pointwise but not converging. Since this, by this definition, we for this interval we could not satisfy this condition, so it cannot converge uniformly. So this is the example which defining both pointwise convergence and uniform convergence and their differences. Now we can look a diagram also. Here we have taken fn x to the power x to the power n. Here if we take f1 is equal to x, so we will get this diagram. f2x is equal to x square, we will get in this way the diagram. So in this way we will get f to the power n, fn equal to x to the power n, this diagram. So all are, we are looking that all are continuous. So all are continuous. But if we look the pointwise convergence sequence fx, which is defined as 1 0 1 for the half open interval 0 1 0 or 1. So here we are looking that it is discontinuous, not continuous. So in case of pointwise convergence, it is seen that the normal or the functions in the sequence can be continuous, but the convergent sequence cannot be continuous. As we are looking at, this is continuous. There are two different points. So this is an example and this is the diagram. If you like these videos, like, share it with your friends, and watch continue. I will try to find out another examples about pointwise convergence and uniform convergence.